Hello viewers, we're now taking you through the story for A-level physics, paper 1. And this video I'm going to go through the topic of calorimetry and in particular specific heat capacity. So this video is under the section of heat and heat properties and is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline of this paper. So physics paper 1 is divided into 3 parts. The first part is mechanics, where 4 questions come from these topics. The second part is heat, where 3 questions come from these topics. The third part is modern physics, where 3 questions come from these topics. So mechanics, the entire part of modern physics was already covered, and now we are on heat, after which we shall go to mechanics. So in total there will be 10 questions in a paper, and the student is expected to answer 5, but not more than 2 from each. So you choose 2 here and 2 here, you should choose 1. Or if you choose 1 here, it will be 2 here and 2 here. If I choose 1 here, it will be 2 here, 2 here, like that. So don't choose more than 2 in any section. And here we are interested in the calculation part of it, but the complete notes are available in the book called Mastering A-Level Physics, paper 1. And if you need a copy, contact the author on any of these 2 contacts. And the complete set of physics has 3 books. There is Physics paper 1, Physics paper 2, and a topical question bank. If you also do principal mathematics, there are 3 books: Math paper 1, Math paper 2, and a topical question bank. If it is subsidiary mathematics, it is only 1 book. And the rest we have O-level topical question bank, O-level physics notes, and O-level math topical question bank. So for you to get any of these copies, contact the author on any of these 2 contacts. So we shall start our topic of calorimetry, and here we are interested in specific heat capacity, or what we call heat and heat capacities. So we shall first look at the terms used. The first term is heat. So what is heat? We shall come and say that heat is the form of energy that is transferred from one place to another due to temperature differences between them. So like I said, we are interested in calculations, but we need some little theory to usher us in the calculations. So here we have to know some of the terms before we go to the calculation part of it. So one is heat, the second one is heat capacity. So heat capacity of a substance is the quantity of heat required to raise the temperature of any given mass of a substance by 1 Kelvin. By 1 Kelvin. So heat capacity can be given by the formula that heat capacity is equal to quantity of heat over change in temperature. That can be written mathematically as, so capital C is heat capacity, quantity of charge is capital Q. So the quantity of heat is capital Q, and change in temperature is delta theta. So if I make capital Q the subject, I'll come up with quantity of heat being equal to heat capacity times change in temperature. So remember that heat capacity is an uppercase letter, because when it is a lowercase, it means something different, as we shall see. So C is the heat capacity, Q is the quantity of heat, and delta theta is the change in temperature. So the SI unit of heat capacity is joules per Kelvin. Another term is specific heat capacity. So specific heat capacity of a substance is the quantity of heat required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin. Remember, under heat capacity, it was any given mass. But when it comes to specific heat capacity, the mass should be 1 kilogram. Therefore, mathematically, specific capacity will be equal to quantity of heat over mass times changing temperature. Mathematically, this small c, when it is lowercase, it is specific heat capacity. When it is uppercase, it is heat capacity. So you should know the difference between small lowercase or small c and uppercase or capital C. Quantity of heat remains the same, mass is m, and change in temperature is delta theta. So when I make capital Q the subject, I'll come up with this. So far we have seen two formulae, one for quantity of heat given heat capacity, another one for quantity of heat given specific heat capacity. So both those formulas are very vital in this topic. So where C is that, Q is that, M is that, and delta theta is that. So the SI unit of specific heat capacity is joules per kilogram per Kelvin, as you can see it here. So the relation between heat capacity and specific heat capacity is that heat capacity is equal to mass times specific heat capacity. That is formula number 3. Then next will be electrical heat supplied. So the electrical heat supplied by an electrical heater will be given by electrical heat is equal to power times time taken. And we know that power is IV, so it can be written as IVT, where I is current, V is voltage, and T is time taken. So that is now formula number 4. So we saw the formula for heat capacity, then the formula for specific capacity, and the formula showing the relationship between heat capacity and specific heat capacity. And now we have seen the formula for electrical heat supplied. So P is that, I is that, V is that, and T is that. So under conservation of energy, we shall see how those formulas we have seen above can be combined to get a formula of interest. So the principle of conservation of energy states that energy is neither created nor destroyed, but can be changed from one form to another. That means that when energy is lost in some from a certain part, it will be gained by another. And that is the main concept under this topic of heat capacities. So you come out that in any system, the quantity of heat energy given out or the quantity of heat energy supplied by one body is equal to the quantity of heat energy gained by the other body. Similarly, in any system, the rate of heat. Now when we say rate of heat, it means power. So the rate of heat energy given out or supplied by one body is equal to the rate of heat energy gained by the other body. We shall see that what that means when it comes to calculations, and let's start our calculations. So question 1 says, came from UNEB 2013 paper 1 question 5C, and says an electrical heater rated 48 watts 12 volts is placed in a well insulated metal of mass 1 kilogram at a temperature of 18 degrees Celsius. When the power is switched on for 5 minutes, the temperature of the metal rises to 34 degrees Celsius. find the specific heat capacity of the metal. So by conservation of energy, what we know is that heat supplied by the heater is equal to heat gained by the metal. Therefore, heat supplied by the heater, we already saw that it's equal to PT, and heat gained by the metal, which is capital Q, is MC, change in temperature. So this is MC and this is change in temperature. So we shall come and substitute. Now for power is here, 48. Then the time, they said 5 minutes to convert to seconds to give you that. Then the mass they said 1 kilogram. That is why there is 1 kilogram there. C is what you are looking for. Change in temperature, you get the highest temperature minus the lowest temperature, or the final minus initial. Therefore, when I simplify, this side I'll come up with this, and this side I'll come up with this, and when I make C the subject, it will be the specific heat capacity they want. So remember to quote this correct SI unit. Then question 2 came from UNEB 2011 paper 1 question 6C and says an electrical kettle rated this is used on 220 volt mains to boil 0.52 kilograms of water. If the heat capacity of the kettle is this and the initial temperature of the water is this, how long will the water take to boil? Now remember, the rating of this kettle is this. It has 240 volt, but it is used on a 220 volt mains. So the reason is that this one helps us to get the resistance of the kettle. So power rating of the heater P is equal to V squared over R. Therefore, we come and make R the subject by taking this side to come up with R is equal to V squared over P. Then we substitute for V squared and also for P to come up with the resistance. Now, because the resistance is constant, it means we can use it for this voltage. So when used on a 220 volt mains, it implies that power supplied by the heater will be V squared over R, and the V is now this one, and the R is this, which is a constant. So the power will now be this. Okay, then we shall come and say that by conservation of energy, heat supplied by the heater is equal to heat gained by the water and the kettle. Remember, the water was in the kettle, and the kettle has a heat capacity, meaning it is needed in the calculations. So you come and substitute the formula. Heat supplied is power times time. We already saw that. Then heat gained by the water, it will be mass times specific capacity of water times change in temperature. Heat gained by the kettle, it will be heat capacity of the kettle times change in temperature. So both the water and the kettle have the same change in temperature. Then we shall come and substitute. Power, we have got the power supplied. The time we don't know. The mass we know here. The heat capacity of water is a constant. It's a constant and it will always be given. Then change in temperature, highest, which is, because they said boiling point of water is 100, that is why I use 100. Then low minus lowest, which is 20. Then heat capacity of the kettle was given 400, change in temperature is the same as this. Now after substituting, next is to simplify. And when I simplify, I'll be able to make T the subject. When I make T the subject, T will be equal to this, and that will be the time they wanted. So now shall go to question 3, which came from UNEB 2009, paper 1, question 5B, Roman 2, and it says, hot water at this and cold water at this are run into a bath at a rate of this and this, meaning that For hot water it is this, and for cold water it is that. At the point of filling the bath, the temperature of the mixture of water was 40 degrees Celsius. Calculate the time taken to fill the bath if its capacity is 1.5 meters cubed. So it means that we have a bath, and here we have hot water coming in and cold water coming in. This hot water is initially at 85 degrees Celsius, and this one is initially at 10 degrees Celsius. And when they mix together at a thermal equilibrium, it will be 40 degrees Celsius. So hot water will have reduced from 85 to 40, and cold water will have increased from 10 to 40, meaning that heat lost by the hot water will be gained by the cold water. Okay. So yeah, come and say that mass per second of hot water is equal to volume per second times density. Therefore, volume per second, remember this is meters cubed per minute, but we want volume per second. So that minute has to be converted to seconds. That's why we divide by 60. And the mass is needed in kilograms. So what we do, we multiply the density, which is kilograms per meter cubed. Okay, so this is volume per second times density to give you the mass in kilograms per second. What about for the cold water? Still use the same formula, volume per second times density. So volume was capital V for cold water over 60 to get the volume per second times 1,000, which is the density of water, and it's a constant. So there you come up with this, which is kilograms per second. Now I have known mass per second for hot water and mass per second for cold water. So you come and say that by conservation of energy, heat lost by hot water per second is equal to heat gained by cold water per second. Therefore, you come and substitute heat loss will be MC change in temperature, and also here to be MC change in temperature. So M1 was for the mass of hot water, C was the specific mass of water, that's why you see they're the same. Then change in temperature, this is change in temperature for hot water, change in temperature for cold water. And M2 is the mass of cold water. So you come and substitute for mass of hot water, specific mass of water, highest temperature which was 85, and final which is 40. Then this side mass per second is that, specific capacity is that, highest temperature is 40, and the initial which is 10. So simplify, the whole of this gives you this, and the whole of this gives you that. And when I make V the subject, V will be equal to that. So our answer is in per minute, because this one was assumed to be per minute. That is why we divided by 60 to convert it to per second. Then the total volume per minute is equal to total volume over total time taken. So this, therefore, total volume per minute will be this plus this. So this was the volume for hot water per minute, and this is the volume for cold water per minute, which we have got. When you add them, it will be total volume over total time taken. Total volume was given the question as 1.5, and the total time is what we want. So you come and make T, simplify, and then make T the subject. And that is what they wanted. Then question 4 came from UNEB 2018, paper 1, question 5D, and it says, the brake linings of the wheels of a car of mass 800 kilograms have a total mass of 4.8 kilograms and are made of material of specific capacity this. If the car is at this and is brought to rest by applying the brakes, calculate the maximum possible temperature rise of the brake linings. So here, like we said, by conservation of energy, here we show that heat absorbed by the linings is equal to loss in mechanical energy. Then we shall quote the formula: heat absorbed by the linings, MC change in temperature, loss in mechanical energy is equal to loss in kinetic energy plus loss in potential energy. Then we shall substitute the mass here. It was this one was given here. Change in temperature is the one we want. Then here half m, mass is there, which is this. Then initial velocity, which is that, and final velocity, which is 0, because they said the word rest. Then we shall simplify and make change in theta the subject, and that will be the temperature rise they wanted. So now we shall go to question 5. Question 5 says, came from UNEB 1994 paper 1 question 5b, and says a copper cylinder is mounted along the axis of a wooden pulley of diameter 0.25. The pulley rubs against the cylinder when it turns. When a steady force of 50 newtons is applied tangentially to the pulley, the temperature of the cylinder rises by 10 degrees Celsius after the pulley has turned through 20 revolutions. Roman 1. If the mass of the cylinder is 0.2 kilograms, find the specific heat capacity of copper. Roman 2. How would you measure the temperature rise? And Roman 3. Give reasons why this is not an accurate method for determining the specific heat capacity of water. So just start with Roman 1. So for Roman 1, we shall come and start by conservation of energy. Heat energy is equal to work done in rotating the cylinder. Heat energy is MC change in theta. Work done is force times distance times the number of revolutions. Then we'll come and substitute for mass, for C is what we want, and for change in temperature. Then here force, distance, and number of revolutions. So distance is the circumference. That is why there is pi d. Then from there we shall look for simplify and make C the subject, and that is what they wanted. So this method is what we call the mechanical method of finding the specific heat capacity of solids. Now Roman 2 said, how would you measure the temperature rise? So the temperature rise of the metal is measured by a short-range thermometer placed inside a hole bored in a solid metal cylinder. So use a short-range thermometer and to place it inside a hole bored in the solid. Then Roman 3 give reasons why this is not an accurate method for determining the specific heat capacity of copper. So one shall say that cooling correction is required. And two shall say that some energy is wasted in doing external work against atmospheric pressure when the metal expands on warming. So now we shall go to what we call continuous flow method to determine the specific heat capacity of a liquid. So here we shall need an illustration. So let us draw an illustration to help us understand what the word continuous flow means. So what I've been looking at has been method of mixtures and electrical method, but electrical method has been involving using a heater. But when you bring in the element of continuous flow, it means that there's continuous flow of the liquid whose specific capacity is required. So let's draw a diagram so that you can easily understand it. So this T1 is the temperature to measure the inlet temperature, thermometer to measure the inlet temperature. This is the thermometer to measure the outlet temperature of the liquid, just say the liquid. Then this is the heater to heat the water, and it has to be connected to a power supply with a PD, so it has a voltmeter to measure the PD, and an ampere to measure the current, and a rheostat to vary the current. Then this is a tap which supplies the liquid whose specific capacity is needed. So this is the liquid, it doesn't exceed this height. So when it tries to exceed, it just goes through the waste. So this liquid will come like this, and when it reaches here, this thermometer will measure its temperature, and we call it the inlet temperature. Then after that, this liquid will go here. So as it passes through this, the heater will heat the liquid. So to reach here with a different temperature, so this thermometer will measure its temperature, and we call it the outlet temperature. Then it can go to be collected here. So this is a container to collect the liquid for a given time. So with that diagram, let's go and try to explain something. So we shall first label this is a constant heat supply, and this is the vacuum, so that no heat loss to the surrounding. This is the heater, this is the beaker, this is the liquid. So the setup is as shown above, which we have already seen the diagram. So the liquid is allowed to flow at a constant rate from the overhead tank. The heater heats the liquid until the thermometers T1 and T2 indicate steady temperatures. So steady temperatures means that the readings are constant. So the inflow temperature θ1 and outflow temperature θ2 are recorded. So this one measured from T1, this one from T2. The ammeter reading I1 and the voltmeter reading V1 is read and noted. Then also the mass M1 of the liquid which flows per second, know that word per second, is determined. Remember, the beaker was collecting the liquid. So at steady state, it implies that the power supplied by the heater is equal to the rate of heat gained by the liquid plus the rate of heat lost to the surrounding. So rate of power supplied is IV, which is I1 V1. Then rate of heat gained by the heater is MC, change in temperature. So MC, change in temperature. And the rate of heat lost to the surrounding is capital H. That is equation 1. So what do we do next? So after that, the rheostat is adjusted to vary the current through the circuit until the inflow and outflow temperatures are the same as before. So they should be the same as before. So when that happens, the new ammeter reading I2 is noted, and also the voltmeter reading V2 is noted. So they should be the same to ease the calculations, as we shall see. So the new mass M2 of the liquid which flows per second is determined. And at steady state, we shall get I2 V2 is equal to MC, change in temperature, times capital H. Think you realize that change in temperature is the same as before. Therefore, equation 1 minus equation 2 will give you this left hand side and this for the right hand side. Then you can factorize out, because C is common and also change in temperature is common, so remain with M2 minus M1, which is here. But our aim is to get C, so make sure the subject will come up with this, and that will be the specific heat capacity. So that is how they get specific heat capacity using continuous flow method. So continuous flow method, in summary, it involves getting two equations and solving them simultaneously. So when you master that, then you are good to go. So with that, let's go through these questions. Question 1 came from UNEB 2020, paper 1, question 6D, and it says, when water is passed through a continuous flow calorimeter at a rate of 100 grams per minute, the temperature rises from 16 degrees Celsius to 20 degrees Celsius when the PD across the heater is 20 volt and the current is 1.5 ampere. That is one set. When another liquid is 16 degrees Celsius is passed through the calorimeter at the rate of 120 grams per minute, the same temperature change. So this is the condition for continuous flow. Temperature change has to be the same. Is obtained at a PD of 13 volt and current of 1.2 ampere. Calculate the specific heat capacity of the liquid. So as long as you see the word continuous flow, just know that there will be simultaneous equations. So let C2 be the specific heat capacity of the liquid and capital H be the rate of heat loss to the surrounding. Therefore, mass of water flowing per second will be M1, which is mass per minute. Now this mass is in grams. It has to be changed to kilograms. That is why you multiply by 10 to the power -3. Then it is per minute, so you have to change the minute to seconds. And when you simplify this, it will give you 1/600 kilograms per second. That was liquid water. What about liquid? So mass of liquid flowing per second will be grams convert to kilograms, and also minutes convert to seconds to give you that. Therefore, by conservation of energy, we already seen this. I1V1 is equal to M1C1 change in temperature plus H. Similarly, I2V2 is equal to M2C2 change in temperature plus H. Now next is to solve them simultaneously. When I subtract, I'll come up with that. Then I substitute I1 V1, I2 V2, M1 C1. C1 is specific capacity of water, it's a constant, and change in temperature. Then M2 C2 change in temperature. So I think we realize that the only unknown is C2. So simplify this to give you that, the whole of this, then the whole of this to give you this, the whole of this to give you that. So my aim is to make C2 the subject and to be that. So continuous flow method, what should be in your mind is that there should be simultaneous equations. Then question 2 came from UNEB 2006 paper 1 question 6B and says, in a continuous flow experiment, a steady difference of temperature of 1.5 degrees Celsius is maintained when the rate of liquid flow is 45 grams per second. So this is grams. And the rate of electrical heating is 60.5 watts. That is one set. Then for the second set, on reducing the liquid flow rate. So here in the previous question, the two liquids have been different, but here the two liquids are the same, but they have just reduced the rate. To this, 36.5 watts is required to maintain the same temperature. So this also temperature change. So this is very vital in continuous flow. Temperature has to be the same. calculate Roman 1, the specific heat capacity of the liquid, and Roman 2, the rate of heat loss to the surroundings. So just start with Roman 1. Let C be the specific capacity of the liquid and H be the rate of heat loss to the surrounding. So initially, that was before reducing the flow rate. What do we have? We have power as this, change in temperature as that, M1 as that, you convert to kilograms per second. So that was initially. What about after reducing the flow rate? We shall come up with P2 as that, change in temperature is the same, M2 is that, convert to kilograms per second. Then we shall come and say by conservation of energy, P1, now previously we have been using I1V1, but I1V1 is the same as is power. So when you have power, you just put P1 is equal to MC change in temperature plus capital H. Similarly, P2 is equal to M2 C3 change in temperature plus H. So next is to substitute or subtract, because I have to solve them simultaneously. So subtracting equation 1 minus equation 2 gives you this for the left hand side, this for the right hand side. So this is supposed to be M1. So P1 is that, P2 is that, M1 is that, C is that, change in temperature is that, M2 is that, C is that, change in temperature is that. Then simplify, this side gives that, and this side gives you that. Then makes the subject, and that's what they wanted. Then for Roman 2, they want the rate of heat loss to the surrounding. So they want the value of capital H. So here I can choose any equation, either equation 1 or equation 2. So from equation 1, this is what I have. I'll substitute for P1, M1, C, and change in temperature plus capital H. Then make H the subject. And that's what they wanted. Then question 3 came from UNEB 2005 per 1, question 5C Roman 2, and it says the continuous flow method is used in the determination of the specific heat capacity of liquids. In such a method, 50 grams of water is collected in 1 minute. So this helps you to get mass per second. Okay, the voltmeter and ammeter readings are this and this respectively, while the inflow and outflow temperatures are this and this respectively. That is one set. Second set says when the flow rate is reduced to this, the voltmeter and ammeter readings are this and this respectively, while the temperatures remain constant. So this is the condition for continuous flow method. Temperatures have to remain constant. Calculate the specific heat capacity of the liquid. So we shall come and say let C be the specific capacity of the liquid and H be the rate of heat loss to the surrounding. Then initially, that is before reducing the flow rate, we have V1, I1, and change in temperature. That was before. What about after? Sorry, before also we need also to convert the grams from the mass to kilograms per second. So we are given 50 grams in 1 minute, which is 50 grams per minute. You have to convert it to kilograms per second. So convert the 50 grams to kilograms by multiplying by 10 to the power negative 3. Then the per minute to per second by dividing by 60 to give you this, which is kilograms per second. What about after reducing the flow rate? We have V2, I2, and change in temperature, which is the same as before. Then the mass, or in kilograms per second, will be 25 grams per minute. So you convert to kilograms per second. So after that, we shall come and say that by conservation of energy, I1 V1 is equal to MC change in temperature type plus H. Same applies to the second experiment, which is I2 V2 is equal to M2 C2 change in temperature plus H. Okay. Now next is solve simultaneously by subtracting to come up with that. Then you substitute I1 V1, I2 V2, M1. Now C1 is C, and change in temperature is that. M2 is that, C1 because it's the same liquid. So it is C because it is the same liquid. Change in temperature. Then simplify, this gives you that, and this gives you that. So it makes the subject to come up with the specific capacity they wanted. Then question 4 came from UNEB 1999 paper 1 question 7c and says, in a continuous flow calorimeter for measurement of specific capacity of a liquid, this meters cubed of the liquid flows through the apparatus in 10 minutes. When electrical energy is supplied to the heating coil at a rate of this, a steady difference of 4 Kelvin is obtained between the temperatures of the outflow and inflow liquid. When the flow rate is increased to this of liquid in 10 minutes, the electrical power required to maintain the temperature difference is this. Find Roman 1, the specific heat capacity of the liquid, and Roman 2, the rate of loss of heat to the surrounding. Then density of the liquid is that. So for Roman 1, we shall let C to be the specific capacity of the liquid and H to be the rate of loss of heat to the surrounding. So density is given, time is that, convert to seconds. So initially, before increasing the flow rate, power is that, change in temperature is that, and volume is that. Therefore, mass of the liquid flowing per second will be that. So the volume times density is mass, but 1 per second, that's why I divide by T. So you come and substitute for volume, density, and time to give you the mass per second. What about after increasing the flow rate? Power is that, change in temperature is that, and volume is that. Therefore, mass per second will be same formula, volume times density over time. Volume, density, time to give you this. Then from there we shall come and say that by conservation of energy, equation 1 is that and equation 2 is that. Subtract the 2 to come up with that, then substitute, simplify, make C the subject, and that's what they wanted. For Roman 2, they want the rate of heat loss to the surrounding. So I use any of the two equations. So if I use equation 1, quote it, substitute, and simplify and make H the subject, and that's what they wanted. So that brings us to the end of this video. Thank you for watching, and bear in mind the next video will be on calorimetry. By this time it will be specific latent heat. So if you're not yet subscribed, please click on the subscribe button below this video so that I can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, such that we can all benefit as a family.